all, welcome in week number 8. I'd like to continue talking about process synchronization. This time I'd like to use the models using finite automata. A short introduction to finite automata or finite state machines. Those are mathematical models of computation, not only computation, also the hardware, using both computer programs and sequential circuits. Those are very basic properties of both software and hardware, having its beginnings in the very first attempts to analyze computers. So it's an abstract which has a finite number of states. For instance, memory cells always in finite number of states. Obviously, every computer has a limited number of cells. Therefore, even having quite a big amount of combinations, the states are finite. The machine is only one state at a time, and it's called a current state. A state can change from one to another, initiated by event or condition. And this state change is called a transition. For example, writing memory, erasing certain cells in memory, or resetting the whole memory of the computer. In mechanical analogies, very simple example of such a finite state machine is a ball pen. When you press, the end, the ball is outside or inside, depending how many times you press. A particular finite state machine or a finite automaton is defined by the list of states also, and triggering condition for each transition. This is n tuple, which is a finite ordered list. In the finite state machine is a part of automata theory. It is somewhere between push down automaton and combinational logic. One of the popular example of such finite state machine is a turnstile mechanical gate consisting of revolving arms fixed the way which allows only one person at a time to pass through. Such activity of this turnstile machine can be represented graphically, in which we have two states, locked and unlocked. And passing from one to another is performed by putting the coin into the machine or by pushing. So if it is unlocked when you push, the machine is locked. If it is locked, you put the coin, then the machine is unlocked. In the software example, also very simple. By the way, you may remember this rule from machine structures. Whatever can be done in hardware can be done in software and vice versa. So assuming a block of codes in the software, and we have certain one state of variables, values of the variables in one state. When certain new data are coming, those data being processed by this block of codes modify state of variables. So depending on input data, we can pass from state 1 to state 2, or supplying another input data, we can pass from state 2 to state 1. Now, we'd like to distinguish two types of finite state machines. One is DFA, which is deterministic finite automaton, and the other one is non-deterministic finite automaton. Every machine can be represented by the n-tuple, so let's have this n-tuple in frames here. So this n-tuple here has 5 elements, therefore it is n-tuple, right? I mean 5-tuple. So elements of this 5-tuple are Q, sigma, delta, Q0, and F. Q is a set of states. In the picture below, those are states S1 and S2. Sigma is a non-empty state of input symbols. Those symbols here below are zeros and ones. Delta is a transition function which takes 2 arguments, a state and the input symbol, and returns a single state. Single state because it is deterministic finite automaton. Here, for instance, if you take the state S2 and you supply input 0, you obtain state 1. Or you may have state 1 and input 0, and then the output is state S2. Q0 is a starting state. Here it is S1. F is non-empty set of final states. Here it is S1 as well. So this is roughly what we have in the deterministic finite automaton. Important is here that the delta transition function is mapping a pair of inputs into just one state. Now, when it comes to non-deterministic finite automaton, all elements of this n-tuple are practically the same, except for delta. Delta, this transition function, takes a pair of inputs, state and the input symbol, but it may return a subset of Q. So may not be 1, but 2 or more states. Here in this example below, you may see that when we take as an input to this transition function P and 1, the output may be Q, or maybe also back a P state. So this is why we call it non-deterministic finite automaton. We will use both in our modeling of process synchronization. Let's get back for a moment to the example you may remember from last class, example of semaphore. You remember that in entry section to the critical section we have P function, and at the output from critical section we have V function. So if we look at this example on the bottom of this picture, you may see that we have a couple of circles which represent states. Let's concentrate on the leftmost circle, in which we have S equals 1, we have not Q, and we have not CS. CS means that some process is in critical section. Q means that there is a Q waiting Q for critical section. Not Q means there is no Q at all. So when we start up, before any process comes to critical section, the semaphore is open, therefore starting state contains the semaphore equals 1. There is no Q yet, and there is no process in the critical section. When the process arrives, it executes P of S function. What's happening with the state? Because a process has come and has been accepted, we have CS now. It's not CS. The state of critical section is CS, which means there is some process in critical section. We don't have still any Q, but semaphore has been closed, saying, oh, informing the processes that they cannot enter until the semaphore changes its state. So the second state after coming of the process is semaphore 0, not Q, and CS. Now we have two options. We may have another process incoming, so we would go to another P of S, or it may happen that if there is no other process, the process which is just being executed in the critical section may finish its execution, therefore leaving critical section, therefore performing function V of S. If this case happens, we have the V of S arrow leading to the initial state, which means if the process left the critical section, now the semaphore is open. Obviously, there is no process in the critical section, and obviously there is no queue. So let's have this situation. So we are starting from the starting state, initial state, and the process is coming. So we move to the second state, which we know already. Semaphore is closed and critical section is busy, so there is CS. Now, if this process takes a while for execution, and in the meantime another process is coming, we change the state. The semaphore is still closed, critical section is still busy, but now instead of not Q, we have Q, because the second process is waiting until this process finishes executing. But if still the process is executing and the second process is coming, the state is not changing because we have still Q. We have still Q. Now two processes are waiting. Semaphore obviously is closed and critical section is busy. If another process is coming, the queue is longer, but it's still queue. So the process state, the rightmost state is still the same as it was previously, which means the semaphore is closed, there is still queue, and there is still some process in critical section. We can repeat several times the same state if new and new process is coming, therefore executing P of S. So this is why the rightmost state has a kind of years of the arrow P of S. But any new process is not changing the state. Only the length of Q is changing. Now what may happen? May happen that the processes are executing one after another. So they execute V of S. So the state, the rightmost state is changing a little bit to the left, but in fact, mathematically nothing is changing because still we have some critical section is being executed, okay, by the process taken from the queue. Semaphore is closed because critical section is busy. So the process did not change because we have at least four processes. So if the next process leaving, we still have the same state because there was a queue. Another process is leaving, and when the second last process is coming, what's happening? Oh, sorry, is the last process is coming. The situation is changing because there is no queue. So in the state, we have still semaphore closed, semaphore is 0. There is a process, and the last process is critical section. There is no more any queue, okay? So the state, second parameter of the state is not queue. And now, once the last process has executed and performed for the last time the V, so the semaphore is open because there's nothing in the critical section and there is no queue. So we can represent the same what we did last class. We can represent graphically using finite automata. Here the state of automaton is S, Q, and CS, those three items. Okay. One state has three characteristics, saying what's happening with S may be 0 or 1, what's happening with Q, maybe Q or not Q, and what's happening with critical section, may be busy, may not be busy. So every state is characterized by three parameters. Let's have example of deterministic finite automata with three states and still referring to processes. We have a function, the transfer function delta described by the table here. So vertically we have states, horizontally we have inputs. States may be 1, 0, 0, 0, 0, 1, and inputs are P or V. Let's start with 1, 0, 0, which means semaphore is open, there is no queue, there is no process in the critical section. But if the process is coming, this process is executing P of S, and the action of P of S is closing the semaphore. Obviously Q is not changing, second parameter is still 0, and critical section is busy, therefore the third parameter now is 1, which is the same as critical section. It means the critical section is busy. Because we have nothing but one process, as you see in the title, one semaphore, so this state 0, 0, 1 lasts until the process is done in critical section. Therefore, process is leaving critical section, and as the process is leaving, it executes V of S. You remember from definition of V of S, if there was no Q, therefore semaphore became 1 and the critical section is 3, so the third parameter is back 0. In the definition of this deterministic finite automaton, we have the same as we did. However, the state have been defined more specifically. So the states are defined as triples, S, Q, and CS, and S may have the values 0 or 1, semaphore may be closed or open. Q may have values 0 or 1, which means there is no Q, which is 0, or there is Q, which means Q is 1. Critical section, CS, is either executing or not. If it's not executing, if the process is not in critical section, the third parameter is 0. If process is executing in critical section, the CS parameter is 1. So this is why we have this table. In the table, you can see that if the state is 1, 0, 0, and if the P of S is coming, on the crossing of the first row and first column, we have the change of the state 0, 0, 1. Obviously, if the process is not in critical section, it cannot execute V of S. So this combination is not possible. This is why you have the symbol of void. If the process has a state 0, 0, 1, which means there is a process in the critical section, obviously V of S may be executed, and as a result, we get back to 1, 0, 0. The characteristic of deterministic finite automata is such that within the cells of those 4 cells of the values of delta of this transition function, we have just one state. One cell, one state. Let's have now, systematically, let's have 2 processes, one semaphore and still deterministic finite automata. And you may see that we have 3 possible states. So 1, 0, 0, 0, 0, 1, 0, 1, 1. 1, 0, 0 means initial states, the semaphore is open, there is no queue, there is no process in critical section. If process is coming, again, as we did in previous example, the process is executing P of S, and the state is changing. It's changing the way that semaphore is closed, now 0, there's no queue, and critical section takes a value 1, because this process is just getting into critical section. Now we have 2 options. The process may leave the critical section, therefore we would go through the arrow V of S back to the initial state, or if the first process has not finished yet, the second incoming process would change the state of the finite automata the way that the Q from 0 is changing to 1. So we have 1 process in the queue, and the state is 0, 1, 1. 0 for semaphore, 1, second one for queue, and third one for critical section. Now, because we have only 2 processes, all we can have now is 1 process leaving the critical section. So the first process, the first one, which arrived first, is leaving, executing V of S, and now we get back to the state 0, 0, 1, because there is no more queue. So the second parameter has changed from 1 to 0. But there is still a second process in the critical section. The first one has left, but invited the second process, which was waiting in the queue. So this is why critical section value is still 1. Now the second process is executing, and once the process is done, it's executing V of S. Therefore, the critical section is left. Therefore, critical section parameter now has changed from 1 to 0, and we are back in the initial state 1, 0, 0. Example of 3 states, only 3 states. We did have general example in the first page with multiple number of processes. Now we have exactly 3 processes. So you can see on this picture below that 1 process is changing once the state, 2 processes and 2 and more processes change, the second process change once the state, but the third process or more processes do not change the state. The first process is just changing semaphore to 0 and critical section to 1. Second process is changing second parameter, which is Q, because the second process is waiting. No process has left, so the second process is waiting. So we have Q. So we have both Q and critical section. Now, if the first process is leaving, we have no more Q, and then back to the first initial. But take a look what may happen. We have something different. We don't have any more DFA, we have NFA, non-deterministic finite automata. And what is the problem? When we have it, it's not a problem. What is the characteristic now of this finite automaton? When we have state 0, 1, 1, which means semaphore, the last one, the rightmost. When we have semaphore close, when we have Q, and there is a process executing in the critical section, the next state depends. Do we have 3 or more, or we have just 2 processes? So if we had more, 3 or more processes, even if one process is leaving, there is still a queue, there is still some process in critical section, and semaphore is still close. But if we had only 2 processes, the process leaving the 0, 1, 1 state is changing the queue to 0. So we have 2 options. From state 0, 1, 1, under V of S, we may have either back 0, 1, 1 or 0, 0, 1, 1. This is why when we look at the delta table, in the third row, in which we have state 0, 1, 1, and in the second column of V of S, we have two options. We may have 0, 0, 1 or 0, 1, 1. This is why this finite automaton is NFA, non-deterministic. And when you look at the finite automaton definition at the left-hand side, you see that the delta is mapping a pair of state and input into power set of states. Power set, which means all possible combinations in general. By the way, you can see that 3 conditions of critical section are satisfied. We have mutual exclusion, we have progress, and we have bounded weighting. It may happen that we have 2 semaphores and the process is passing through 2 semaphores. When we have 2 semaphores, in general, a certain new situation may happen, which is a deadlock. It's something like 2 people meeting on narrow stairs and passing through opposite directions. So the subject of deadlocks I will comment on the next class. However, you have here a relatively simple picture of such a situation using finite automata in which we have 2 semaphores. So the state here, when we have 2 semaphores, is made of 4 elements. Q, 1 semaphore, S, second semaphore, critical section, and maybe busy waiting. You may remember from the previous class that if you have 2 processes, one process may prevent second process against accessing critical section. So the second process is busy waiting. Here the situation is such that we have 2 semaphores and corresponding finite automaton model is relatively simple, but I will comment on deadlocks in more details next class. Let's have problem solution attempt using DFA. You remember this algorithm number 1 from the first class. Remember that in algorithm 1, only one turn variable has been used. And you see when the process 0 is coming to execution, before do loop, the state of this process we call not ready. It's just before critical section, even before the entries section of critical section. So it's not ready yet. Maybe somewhere else, maybe reminder section, maybe at this point of the program. In both situations, the state is not ready. Then the process enters into the if the turn value was not equal 0, the process would wait, okay? Because this is for the process 0. But obviously, process 0 is 0, so it's not waiting. And after executing critical section, it sets turn into value 1, and it is now from the sims now it is not ready. In process P1, if turn is equal 1, the process cannot execute again, as you can see. If the process P1 was not ready, did not want to enter critical section, but P0 would like to, do while loop is in busy waiting state, because indeed turn is not 0. So the only situation possible now is that the next is process 1. And the same, once process 1 is 0, is done and sets turn into 0, the process P0 can execute. So you see that you remember that in this wrong solution, the turn variable forces the processes to be executed in alteration. Let's take a look on finite automata model. It's starting on top with the start arrow, and at the most beginning, let's assume that both processes are not ready. Now, depending on turn, if turn was equal 0, the process P0 can execute. Therefore, P0 has a state critical section. P1 obviously must wait, is busy waiting. If, so the first component of the state is the status of P0. Second component of the state is status of P1. And this status may be not ready, busy waiting, or critical section, as you remember. So if both, again, if both processes are not ready, but turn variable is 1, the P1 can be executed. P0 is busy waiting, of course. So turn 1 is leading to the new state in which P1 is in critical section and P0 is busy waiting. Now, if you want to check, if you want that another state, another process is in critical section state, we have to apply in alteration turn 0 and turn equals 1. So what does it mean? If you are in the state CSBW, which means P0 is being executed, the only arrow which allows to leave the state and continue working on the whole software, we have to wait until turn is equal 0, because the only arrow leading from CSBW to BWCS is turn equals 0, and vice versa. If the process P1 is being executed now, the only arrow which leaves this state is the arrow with turn equals 1. So as you see, the change of statuses, which means the only possibility that both processes are allowed to be in critical section is when they are executed in alteration. P0, P1, P0, P1, and so on. And this is visible, very clearly visible on this graph. There is the only arrow leading from CSBW state is the arrow which symbolizes turn equals 0. The only arrow which leads from BWCS state is the arrow with the value of turn equals 1 in alteration. There is no other way out of those processes. So if the process P0 is being executed and turn is 1, obviously the the second process cannot be executed. It lasts a long time. Let's have algorithm number 2, and this was an attempt of using flag 0 or flag 1, which say the process is ready. So you remember from algorithm number 2 code that, for instance, in process P0, we have do loop, and before statement flag to be true, we have not ready. So until this moment, process is not ready. The process is ready only if its flag is true. And once the critical section has been executed by the process, flag of 0 becomes false, allowing maybe other process to perform. Let's take a look on the graph. We start with an arrow, and let's assume that we start with both processes being not ready. And again, first component of the state is a state of P0, second component of the state is a state of P1. So if we start with both being not ready, we have two arrows which leads from this state to another state. So if the flag of 0 is true, the flag of 1 is false, obviously the process P0 is allowed to critical section. The second process is still not ready. If we start with state not ready, and flag of 1 is 1, flag of 0 is 0, we have input ft, means that process P1 is allowed to enter critical section. And those states can be now changed in between, because we have two arrows leaving from critical section NR, CS, NR state, and we have two arrows leaving NR, CS, which means we are not stuck. We can change the status from CS NR to NR, CS two ways, either f of t or f of f. Those two states allow to circulate states of processes the way that they can execute their own critical section. But we have one problem. If both processes arrive exactly at the same time, if they arrive at the same time, you may see if both are ready at the same time, which means the inputs are T, which means flag of 0 is true, flag of 1 is true. If they both arrive at the same time, both are in busy waiting. And you can see that on the bottom, this state BW on the bottom of the graph has no any arrow leaving this status, which means both processes are stuck. There is no escape from this, and this is a problem. But now, when we have finite automata modeling, you can clearly see that here, this BW status or state on the bottom is the finite state, because there is no arrow leaving or changing this state to any other. The processes got stuck here. So you remember that there was Peterson's problem solution, in which we use flag 0, flag of 1, and we use turn variable. When you look at the graphs, you may see that the transitions which means the meaning of arrows are the first component is flag of 0, second component of the transition is flag of 1, the third component is turn. When you look at this graph, you can see that there is no situation as we've had in algorithm 1 and algorithm 2. There is always some arrow leaving every state of synchronization. We have here 5 states, and all those states have 2 arrows leaving the state and leading to another state. You may also see that 4 states, except for the starting status, all states have critical section situation for P0. So upper 2 states have critical section at the first position, which means P0 is in a critical section. 2 lower states represent situation in which P1 is in the critical section. And we have all possible interconnections between those states, which means if process 0 is in critical section, there is a way through the arrows to reach the state in which P1 is in critical section. So for instance, if we have the left upper state critical section not ready, which means P0 is in critical section, you can go, for instance, to not ready state, and then back to busy wait critical section. So the second process P1 is busy. So they are not get stuck, and the same process may execute several times. For instance, if you take into account 2 upper states of synchronization in which the process P0 is in critical section, you can pass from, if P0 is coming repetitively several times, we have a way to pass and execute again this process. So the upper arrow T0 is leading to the process, the same process P0, or you may go through NR and back to CSBW. So you have 2 ways of passing to critical section if process P0 is willing to be executed twice or several times in a row. So there is no alternation necessary. And this is the case of every state. Every state may pass to every other state following certain arrows, one after another. So, in conclusion, that the critical section problem requirements are visible. Mutual exclusion is satisfied because there is no state critical section. There is no situation in which both processes are in critical section. There's a progress because if we have busy waiting state, it's always followed by critical section state. And we have bounded waiting. So if the process in busy waiting state, it is allowed instantly critical section after other process leaves critical section. So all those properties are clearly visible on the DFA diagram. So please try to analyze exactly, step by step, in details, every of those diagrams to make sure that in which diagram the critical section problem requirements are satisfied. So this is clearly visible here in the Peterson's solution. Try to analyze the same way which of those three critical sections are not satisfied in algorithm 1 and in algorithm 2 with graphical interpretation of those finite automata graphs. So this would be all for today. Thank you very much.